Ready?
Yep. Let's do it.
Ready?
Yep.
Okay. All right. Hello, everyone. Welcome to today's brand new episode of Corecast. I am your host, Tim.
And this is Sahil. Welcome, everybody, to a brand new exciting episode of Corecast. If you haven't already, do join our Discord channel. And if you're watching this on YouTube, where we have been mostly successful in doing this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode and we'll get to them. So without further ado, Tim, let's get to it. So, Tim, I was watching this one YouTube video by popular channel. I can't quite pronounce the name. I think it's like Kurus Gats. I apologize if I'm mispronouncing the name. They talk about this interesting phenomenon called like strange matter, which is very strange in terms of the name and how it's like the most dangerous substance in the world and or universe and whatnot. So I guess like before we delve into like all that stuff, I kind of wanted to first like talk about like what does strange matter mean? Isn't there like one type of matter like electrons and protons of this table? Like why is there a distinction called like strange matter? Is one question.
Yeah. Oh, 1 second. Let me make sure that the sound is on.
Okay.
Okay, I think it's on. Yeah. Let me first say that statement is absolutely sensationalist. And indeed, there is something such as strange matter, but it's not as well. It is strange, but it's probably not as strange as you might think. But at the same time, there's also stranger matter than strange matter, and we'll get to that later. But maybe a little historical context is needed. Yeah. So it's roughly 100 years ago that Rutherford started this whole almost like a subatomic physics when he discovered the particle proton, right? And it's kind of amazing that was just 100 years ago. We didn't even know all these other things, but it all started when we discovered the protons, and through radioactive decays and cosmic rays, people discover an array of different particles, things like electrons, the neutrons was discovered, and then the anti-particles, cousins of electrons and protons and neutrons, they were also discovered. And in the beginning, it was very, very confusing because it turns out that there are actually many, many different particles, and some of which are not as familiar to our listeners. For example, they discovered the pions, right? It turns out to be made up of quarks, but they didn't know that. They just found some new particles called the pions, and they also found some particles called the muon, right? Which has similar properties for the electron, but it's just a very strange. They just found it coming from outer space. It's just going through their detector, and it doesn't fit any existing description, so they have to give it a new name, the muon, right? And all this was very confusing until recently, I think maybe in the 60s and whatnot, where they finally were able to unpack, why are there so many types of particles? And they were finally able to write down kind of like a periodic table for all the fundamental particles. And it turns out that many of the particles, things like protons, neutrons, pions, and kaons that they discover, were made of something we call quarks, right? So the familiar types, protons and neutrons, are made up of mostly up and down quarks that we know. And this is where the strange matter comes from. It turns out that there are actually a few more quarks than we've seen in daily lives. And this is just a brute fact of our world. Like nobody, you can't really ask the question, well, how come there are more? But there just are, right? It turns out that there are strange quarks, and there are charm quarks. We'll talk about these. Top quark and down quark. These are extra quarks. And but stuff that's made up, that consists of strange quark, ends up having the name strange matter. So, but really, there is, you can make stuff out of charm quarks, or the bottom quark, or as we'll talk about more later, you can't really make stuff out of the top quark, but the strange matter is just the first glimpse into matter beyond the stuff that we see in our everyday world.
Huh. So okay, so if I'm to kind of go trying to summarize what you said, essentially there's like more to the universe than just electrons and protons. There are these, different sets of particles. And I think you mentioned the word families, right? Did I hear that correctly?
Yeah, maybe. Yeah, so there are many different phrases. I think family is one way to categorize them. It turns out that these particles, you can group them into, like, kind of organize them into columns, I guess, like the periodic table. There's like the noble gases and the stuff like that. You can organize them into families, or sometimes I think they're called generations. I think it depends on how you, depending on the convention. Yeah. So loosely speaking, there are 3 families or 3 generations of particles, and yeah, so that's why. So for the quarks, you have up down. That's family number 1. There, and then there's the strange and charm. Actually, I should probably reverse the order. Charm and strange, and we'll explain why. That's the second family, and then the top and the bottom. So that's the third family. So we now know that these matter particles comes in exactly 3 distinct types, right? And remember, these are just brute fact of our universe. It just is.
Mm-hmm. Okay, so essentially you can break all the quarks that we've seen into 3 generations. And I guess, like, what constitutes a generation? That seems kind of like art. Is it really like arbitrary, or is there some like logic to the madness of like saying, okay, I'm going to segment out these particles into one generation, these other particles another generation? Like, yeah, is it ad hoc, or is there some like method to the madness?
Yeah. I mean, when they were first discovered, people were very confused, right? When they first discover the strange quark, of course, they didn't directly observe the strange quark. What they observed was stuff like, for example, protons are made up of, roughly speaking, 2 up quark and the down quark. It turns out that in an accelerator, you can kind of grab, let's say an up and a 2 up, but instead of a down, you could replace with a strange quark. You could do that. Then you kind of created a strange version of the proton. Of course, it's not called a proton anymore. But the fact that you can do that tells you that strange quark, despite the fact that it's stranger, actually has very similar property to the down quark, right? And experiments again and again have shown us that, even though the matter is different, it actually has essentially the same property as the down quark. So even though it's strange, it's actually not that strange. So so there's sort of this dictionary that goes, right? So the strange quark is very similar to the down quark, and the charm quark is also very similar to the up quark. And you could and every extra quark also has kind of this dictionary. Like the top quark is very similar to the up quark in terms of the interaction with the forces, and the bottom quark is also very similar to the down quark, and vice versa. So now we know that there's some reason behind the madness, right? Like the 3 families it's not just a random scrambling of it's not just a random table. It's not just some random taxonomy, right? There is structure to the madness. 3 families is 3 families. It's legitimate.
I see. Okay, so what you're saying is that, like, in these 3 generations, you have like 2 quarks in each one, up down, charm strange, top bottom. Um and so and my question is, so now you made an interesting point that, like, say the strange quark is similar to the down quark and they belong to 2 separate like generations or groupings. Why don't we see in nature like a strange proton, as it's called, where you have like 2 ups, but the down is now replaced by a strange? Like, and just, I mean, you're effectively saying it would basically be the same thing, right? Or is there actual difference?
There is actual difference. And you bring up a very good point. Like, sure, you told me that a strange proton is the same as a normal proton. Otherwise, like, why the hell do we don't see like strange, I don't know, strange Sahil, right? Made of strange carbon, right? That would truly be odd. But we don't see that, and that is actually thanks, or I guess no thanks to the weak force, right? And I know this is perhaps somewhat unfamiliar to our listener, but the weak force is a force that allows the type of particle to change. And so this is, here lies the key difference between these families now. So in terms of forces, they're exactly the same, except that their masses are different. You might ask, well, mass is big deal, So the strange quark turns out to be quite a few times heavier than both up and down quark. Now, what gives then? In quantum physics, generally, there's a rule of thumb that says anything that could happen, at least within reason, will happen. So if this weak force allows species to change, well, let's see what the strange quark can change into. Because strange quark is so similar to the down quark, it can actually decay into the down quark. Actually, it decays to the up quark, but ignore that subtlety for a moment. It can actually decays into the other lighter quarks, right? Mm-hmm. And if the strange quark was lighter, that would not be possible because there's not enough energy to do that. So even though quantum physics tells you everything that could happen will happen, it has to be within limits, within the limits of the physics law. So that comes back to a good point. Like you say, well, how come we don't see strange quark, charm quark, top quark, and bottom quark? Well, it turns out that they're just a little tad too heavy, and because of their slight heaviness, they decay into other stuff. They don't live long enough for us to see its existence. But if it wasn't for the weak force, there will be strange protons and other strange matter, I guess.
Huh. Could you explain to the audience, I guess, like maybe dig a little bit deep into like why is it that heavier particles decay into like lighter ones, or in the sense in like these heavier quarks decay into these like less heavy quarks? Why can't it be the other way around? Like I hear all about this quantum fluctuations, like energy appearing out of nowhere and then disappearing. Why can't like a lighter quark turn into a heavier quark and like just stay that way?
Yeah. I think you can intuitively understand this fact. Even though, in quantum physics, you can kind of borrow energy for a little bit, you still have to return it. So imagine the scenario where let's say I have an up quark trying to transition to a strange quark. I mean, it does kind of happen if you look at the equations. But what happens is when that happens, there's an energy deficit, right? Because it has to borrow energy in order to increase its mass. So after a fraction of a second, it has to return that favor. So it cannot really successfully do the transition. Now look at the other way around. When a strange quark decays, it's very happy to shed some mass, convert that into energy, and actually it will decay into a different quark, and it will also create some other particles, but let's not get into details. I mean, neutrino is one of them, and electrons. When that happens, those energy are lost through those other particles, and they leave the system because they fly away near the speed of light. So now it's really hard to return that energy anymore. It's like imagine, I don't know, like you just drop 3 money on the highway and everyone just up for grabs. Take that money. They're running away. They're not returning it back, right?
That's fair. Yeah, that's an adequate analogy. I guess okay, so we have this thing in which so I'm assuming that each generation is like heavier than the last. So like up down, which make up, protons, neutrons, the matter we see most commonly, at least us, are made of up and down quarks, which are the lightest pair of quarks. Then the next heaviest quarks are charm and strange. And then the next ones is top and bottom. Is my understanding correct on that?
Yes, that's exactly correct. And I mean, if you ask me why, I can't really tell you why. But this pattern actually repeats. And what I'm telling you, just purely observational. It just is true. And it is really one of the deep mysteries of the universe. Why such a pattern? But let me tell you this, the conspiracy goes a little deeper than that. Because not just for quarks, actually, for what we call the electron or the lepton family, the same pattern occurs, right? So you have the lepton, you have the electron that everyone knows, and there's also the electron neutrino that you people might be less familiar, but they're like the lighter cousin of the electron, but it doesn't have electric charge, so it passes through us. Our previous episode covers some of that. It turns out that they also come into families, just like the up and down quark, right? So the second family, it's a little heavier. It's made up of the muon and the muon neutrino. And there's also the heaviest one. It's made up of tau and the tau neutrino. So these guys also come in 3 families. And it's no coincidence, at least we believe, that the quarks have 3 families and the electrons also has 3 families. But keep this in mind that there does not need to be an inherent reason why these 2 seemingly different types of matter, you mean like, like protons and neutrons, they're kind of different from electron, right? There's no reason they need to have the same structure. But man, this is very tantalizing. It seems like nature, there's something going on in nature.
Yeah, actually, so one thing that's come up in our conversation over the past 15 minutes or so has been the number 3, like 3 generations in both the quarks and the leptons, the electrons and muons and tauons, and then also the 3 families of quarks. Why is it the number 3? Like, that seems like, couldn't it have been 4, 5, 10? Like, is there any reason why it's 3?
Yeah, that is a very good question. So physicists have postulated that maybe we just haven't seen the 4th one. But that turns out to be not the case, right? And for a variety of reasons. And keep in mind that these are what I'm going to tell you, these are observational physics. These are just observations, right? So one thing you can do is you can go through Einstein's equation to see how fast the universe was expanding. And particularly in the early universe, when the universe was just a plasma, you can look at the way the plasma is cooling and whatnot. You can look at the way the galaxies are and what we call the cosmic microwave background. Basically, you can study the pattern of the afterglow of the Big Bang to look at how fast the universe was expanding. It turns out that depending on the number of neutrinos, it will impact the rate of expansion. And from that observation alone, you can conclude that there were 3 types of neutrino, roughly speaking. It's just a brute fact. You can just do that. And a different experiment you can run is you can grab one of these, and this is very very much particle physics phenomenon. You can grab one of these heavier particles, what we call the Z boson, but just ignore that for a moment. This is kind of like a force carrier type particle. And it's able to decay to all kinds of particles. So it doesn't care about family. So basically, it doesn't bias towards any particular family. It's happy to decay to all types of families. And when you look at how often this Z boson decays to other stuff, you measure that it's 3. There are 3 types that it decays into. So for example, these 2 numbers, there's no reason they need to be the same, but they are exactly the same. So it points, so observationally, experimentally, it's a very solid conclusion that yes, so far we see 3. And then theoretically, also that you can't really add an extra one. So the number 3, I think, is pretty concrete. There are 3 generations, but in terms of why there's 3, like, does it have to be 3? Why not 4, 5, 6? I can't give you a good answer. I really don't know.
Yeah, that makes sense. I mean, your explanation makes sense. Like, you observe 3 based on experiments, but it is not. Yeah, it makes sense that it's not also clear. One question I have is, like, I guess you mentioned that, like, that there's difference between these three generations, both for quarks and for leptons, that each successive generation is heavier than the last. In terms of particle physics, what does that translate to? Like, is there a deep reason why all three generations are not the same? Is that by accident, or is there some mechanism behind that?
Yeah, it is not really by accident, but like so far I keep telling you like they're the same. Of course you say, well, what gives? They are different at the end, and there's kind of a bad actor, and it is indeed a mystery, and some of your listener might have guessed already. This bad actor is the Higgs boson. So you might have heard that the Higgs boson gives particle masses, and that's exactly what it is. So it's almost like, imagine it's like you have a massive family with like triplets, or I don't know, brothers and sisters, right? Everyone, it's like fair, they share everything, they share all the food, their toys, whatever, the inheritance, I guess, okay? But then there's this like terrible uncle, like the Higgs boson, that just treats all three families just slightly unfairly, right? So the Higgs, for some strange reason, somehow prefers, let's say, I guess if I use prefer in terms of interaction, that the Higgs has the highest interaction with the third family, so it makes them really, really heavy, right?
Mm-hmm.
So it has the second preference to the second family. It's slightly less heavy. Of course, family 1, 2, 3 is arbitrary. It could have been 1, 3, 2, right? We just order them in terms of which one's heavier. Yeah. But it turns out that, the Higgs just universally favors the third family a little bit more than the second one and then the first one. So in some sense, the reason we exist is because the Higgs field, because it's really what's giving the mass, just doesn't like our ordinary stuff that much, so that we don't decay. So really, that's the reason. So the reason why normal stuff is made up of up and down quark, electron and electron neutrinos, is just because we just is less favored by the Higgs field, and that's the only thing that's different so far.
So actually, this brings up another question. So it seems like, based on what we were discussing before, that heavier stuff decays into lighter stuff. Is it the case that if you interact more strongly with the Higgs, you have a like greater chance to decay into stuff that interacts less with the Higgs? Like, what's going on with that?
Yes, indeed. So the Higgs does have a preference to decay into heavier stuff. That's the only particle that we know that has that bias in the particle physics model. So the Higgs is it's an odd one.
No, I was referring to particles that interact more with the Higgs are more massive, and so but they decay into like lighter things. So for instance, like you mentioned you see like charm and strange decay into like up and down, for instance, but the charm and strange, since they're heavier, interacts more with the Higgs, but then it decays into something lighter, which by virtue of it being lighter interacts less with the Higgs.
Oh, so is it... I see what you mean. Yeah, but the thing is, when you talk about decay and stuff, those happen through the forces, right? So the forces don't care about the generations, only the Higgs. I mean, of course, in quantum physics, anything that could happen, right? A particle could decay through the Higgs boson, but that happens very, very rarely. The chance for that happening is very, very tiny, so it's negligible. It's even weaker than the weak force, basically, if you calculate the probability. So roughly speaking, in terms of decays and just ordinary forces, all three families are the same, except the Higgs, which is not really a force, but...
Yeah, so three families, they have each, so to summarize, three families, they have increasing mass as you go from one generation to the next. Increasing mass means they interact more strongly with the Higgs. I guess then, like, can you imprint, like, at least based on this current model of it getting heavier and heavier and heavier, can you have a fourth generation, or are we stuck at three?
Apparently, I think I wouldn't say it's totally impossible, but I would say probably not, right? Because in order for
Hmm.
us to have a heavier family, you need something new that interacts with the Higgs even more. And we know that the top quark, it's already almost at the limit of on how much it loves the Higgs boson. I mean, you can't give it too much love. Otherwise, when you have too much interaction, kind of the particles kind of mess themselves up because of quantum physics.
Mhm.
So there's some theoretical constraint that says that it can't happen. And also through experimental observation, remember, if there's a third family, the neutrino, it would not be present in the beginning of the universe. So,
Wait, fourth family, or you said third family?
oh, sorry, yeah. If there was a fourth family, the fourth family neutrino could not have been present in the beginning of the universe because we measure how fast it expanded. So from
Mhm.
those reasons, if there was a fourth family, right, beyond the third one, it wouldn't exactly be the same family anymore, right? It will be somewhat different. So the number three really is three, I think.
Ah, okay. I guess like what happens like to the best of your ability to explain at a layperson level, what would happen if you like have like more families? Just yeah, like what would happen to the universe if we just had more families of things?
That's a very good question. Actually, I reckon that if you have more families, things actually would not change that much, honestly.
Oh.
Right? Because think about it, in our everyday lives, I mean, of course, the rate of expansion might be a little different, right? The way the universe created itself would have been a little different. But I'm sure you can tweak the numbers up and down a little bit and still have a viable universe to exist in. And that's what makes it really a mystery, right? Because our existence is mostly contingent on just one family, one out of the three. Before their discoveries of the second and the third family, we really didn't care. That's why I think there was a famous phrase. I forgot which physicist it was due to. When they discovered the muon, I don't know, was it Feynman or something? Someone said like, "Who ordered that?" Like, what the heck, right? It's just kind of a surprise, right?
Yeah.
So yeah, the universe really would not. I mean, of course, the universe would be different, but I don't think it would have been catastrophic for life or for the existence of the universe. In fact, let's hypothetically consider a universe where we don't have the weak force, let's just say.
Mhm.
Then all these families of particles would coexist. There would be strange protons, there would be charming proton, there would even be top and bottom protons and neutrons. Man, in terms of atoms, we could have an atom made up of a strange proton and a muon. That could have happened. That would be kind of like a crazy zoological universe with so many different combos of particles. Maybe it could even create like more interesting life form. Who knows?
Huh. I guess what do you see the issue with that? Like if that were permitted by the universe, at least this universe that we exist in, what would that mean? Like I'm just curious. If we're now entering more speculative territory, but what would you say like if things couldn't decay? Like just everything was just there.
Oh, I mean, of course, yeah. If things could not decay, I mean, it's hard. Like you can't really get rid of the weak force because if you do that, you actually will have runaway fusion. That means,
Oh.
yeah. So maybe it'll be okay. Maybe it won't be okay. So inside stars, fusion can just happen again and again and again and again. It might still reach a critical point. We could have very strange stars. Um, Actually, I'm not sure. The universe definitely will be interesting. I don't know if life as we know it will exist, but there could be different forms of interesting structures. Certainly, we'll have more diversity, right? You could have like a nuclei with like 20 strange quark, like like 20 strange baryons, some protons, neutrons, and a mishmash of quarks, he'll be really weird, I would say. I'm not sure.
Yeah. Actually, what? So, kind of going on along the lines of speculative territory. I remember when we were in discussion for this episode, we had talked about something involving extra dimensions you wanted to mention. Do you remember what that?
Oh yeah. So one of the deep mystery was why 3 generations, and why is the Higgs so different? You know, how come everything else is the same, but something else is different, right? So physicists have thought about ways to explain this. One possibility is that, you know, of course, the starting point is always that, you know, we truly, like, if you were to hold a gun to my head, I'll probably tell you that, look, these 3 families probably is an illusion, right? And apparently they look different, but that's just because the way the universe is. But deep down inside, a strange quark probably is no different than a down quark, right? That's what I truly believe in, of course. But personal opinion aside, well, then you can ask, well, how can they accommodate these differences? One possibility is you can link it to geometry. You can imagine perhaps there is some extra dimension that's very small that we cannot see, and somehow these particles, these quarks, or these electrons and neutrinos, maybe they live in this extra dimension. And it's just that their shape just happens to be a little different from each other. And that's what caused these properties to be a little bit different. And maybe the Higgs boson also lives in this extra dimension, and that's why it has this bias, because it feels differently toward different families, because they, you know, it's almost like you have a different address in this extra dimension where the 3 family lives. So they grew up a little differently, right? Different neighborhoods in this extra dimension, right? So that's one potential explanation. That's still a very palatable one, I would say.
So you're saying that if there were extra dimensions, then the geometry of these particles in these extra dimensions would influence the interaction with the Higgs, which gives rise to this notion of like a different mass, which then translates into different generations. Is that
Exactly. Yeah, a good analogy is like extra dimension, or think of it as a different vibrational mode, like different note in the music. So then so the frequency dictate their mass, so they're a little different. Yeah, so that's a nice way to think about it.
Yeah. Actually, yeah, that makes sense. I guess is there an intuitive way to explain how geometry influences interaction? Like, you actually brought up an interesting connection that how things are shaped abstractly, of course, influences like how they interact. Is there like an intuitive way to explain that?
Yeah, I guess there are multiple angles. Like for example, the musical instrument analogy is actually quite good. You know, it's just you know, if you have the same instrument, if you tune it differently with different tension, you plug them, you know, they can produce different musical notes, even though it's the same thing. So it's a very good analogy. So you can think of kind of let's say the fret of the guitar as an extra dimension, and it's really, you know, because particles are waves, they can live in this musical dimension, kind of just have different vibrational modes, and that gives different mass. Another analogy that I would like to give is that of a magnet. At first glance, it seems a little different, but they're actually not so different analogy, right? So if you grab a magnet, right, the magnet has an orientation, you know?
Yeah.
But you can't honestly, like, imagine I have a magnet on my hand that the North Pole points up, right? You can't honestly say that the universe somehow has a preference of up, right? Because the magnet has to choose a direction. If you zoom in microscopically, you see that inside this magnet, there are these little chunks of domain. And most of them are random, but just by chance, it has an orientation one direction over another, it causes the magnet to have an overall orientation. And you can imagine quantum mechanically, all three families could be one of the same chunk of magnet. You can imagine it that way. But then maybe different parts of it just by chance have a different orientation. And as a result, different parts of it have a slightly different interactions, right? And also this has kind of like a extra dimension vibes in it. You can be like, well, where does this magnet live? Well, it's not going to be ordinary space. Maybe it's like an extra dimension. So these two are kind of related analogies that physicists like to use to explain things that look the same but are apparently different. If that makes sense.
Yeah. I can see how those two are connected. Yeah. We have an audience question. That like, does this three generation? I think this is what the audience is referring to. I'm going to paraphrase the question. Does this three generation thing reinforce supersymmetry?
So supersymmetry is a concept that we probably won't get to. Maybe one day we'll get to it. But it's independent of this fact, right? Even if you have supersymmetry, you still have to think about, well, how come there are three generations? So this three generation exists orthogonal. It's a different idea in terms of supersymmetry. So I don't think I will get too much into that. But yeah, three is three. Whatever physical theory you have, somehow there are three copies of matter. I don't know why, but three is three.
Yeah, and I mean, can we say, can we rule out the possibility with a high likelihood that like we don't see any like lighter quarks or any quarks in between the generations?
Yeah, so we absolutely don't. Yep, we absolutely don't see them, because if there were lighter ones, we would have produced them in the lab, and the universe would have created them in the beginning, and we would have some hints of those. So there's no lighter ones. And they also can't get that heavy because it'll mess up the Higgs boson. So 3 is 3. So why 3? Really 3? But that's a different question.
I see. To go, maybe this might be slightly in the weeds, but I'm wondering, for the case of, so we've discussed the case of quarks. For the case of leptons, like electrons, muons, tauons, can you have a fourth generation?
I think experimentally, there may be a little more room, but still the same issue will apply. You still have the problem, well, if you have a fourth generation, you probably have a neutrino, and neutrinos are extraordinarily light. Because they're so light, it should be easy to make them. But we have not seen them created. So if there's a fourth generation, it's gotta be... It's going to be like fourth generation plus something else. So it's not going to be... It's going to be a little awkward. I don't think it will be exactly the same as the other generation. So I think 3 is a really pretty solid number.
Okay. I do like the number 3, so I'm good with that. So I guess we're almost at time. Is there any parting words you want to leave the audience with about these 3 generations?
Yeah, I guess coming back to the initial point, like if you Google a lot of articles about strange matter, yes, there is strange matter made of strange quark, but that's not the strangest thing. Actually, there are way stranger matters made up of charm quark, bottom quark, and well, possibly top quark, but there's a reason why. It's too heavy to make stuff. Basically, top quark is just a little too heavy. So really, the strange thing is not strange quark. It's the fact that, every particle we know has kind of like a 3-fold duplication. We don't know why. And it's really a deep mystery. And I really hope that we can answer the why one day. But it's kind of remarkable that it was only like less than 100 years ago people discovered that protons exist. And we've gone a long way from protons to like the particle zoo. And I really hope that in 100 years we'll find out you know, maybe we'll find out more. Maybe we'll answer some of these mysteries, but really hope I can witness some of that.
Yeah, I hope so as well too. So well, on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah. See you all next week. Bye.